In the last video, I reviewed the hash set, and as I've said before, that ordering is unspecified and generally chaotic. If you need an ordered set, you'll want to consider either the linked hash set or the tree set. A linked hash set maintains the insertion order of the elements. The tree set is a sorted collection, sorted by the natural order of the elements, or by specifying the required sort during the creation of the set. The linked hash set extends the hash set class. It maintains relationships between elements with the use of a doubly linked list between entries. The iteration order is therefore the same as the insertion order of the elements, meaning the order is predictable. All the methods for the linked hash set are the same as those for the hash set. Like hash set, it provides constant time performance O1 for the add, contains and remove operations, but like the hash set, this assumes an efficient hashing function. A tree sets class uses a data structure that's a derivative of what's called a binary search tree, or B-tree for short, which is based on the concept and efficiencies of the binary search. I've discussed the binary search method on list, as well as the java.util.collections class, and shown that this type of search is very fast if the elements are sorted. This search iteratively tests the mid-range of a group of elements to be searched to quickly find its element in a collection. As elements are added to a tree set, they're organised in the form of a tree, where the top of the tree represents the midpoint of the elements. This slide shows a conceptual example using some of the string context from my last samples of code. Further binary divisions become nodes under that. The left node and its children are elements that are less than the parent node. The right node and its children are elements that are greater than the parent node. Instead of looking through all the elements in the collection to locate a match, this allows the tree to be quickly traversed, each node being a simple decision point. Java's internal implementation uses a balanced tree data structure called the red-black tree. This class isn't about software engineering, but if this topic interests you, let me encourage you to explore software data structures. The main point is the tree remains balanced as elements are added. If you want to dive deeper, I do have another course just on Java data structures and algorithms. Remember that big O of 1 is constant time, meaning the time or cost of an operation doesn't change regardless of how many elements are processed. Big O of n is linear time, meaning it grows in line with the way the collection grows. Another notation is big O of log n, which means the cost falls somewhere in between constant and linear time. The tree set promises big O of log n for the add, remove, and contains operations compared to the hash set, which has constant time big O of 1 for those same operations. A tree set can be declared or passed to arguments typed with any of the interfaces shown on this slide. This class is sorted and implements the sorted set interface, which has methods such as first, last, head set, and tail set, as well as comparator. This set also implements the navigable set interface. As such, it has methods such as ceiling, floor, higher, lower descending set, and others. I'll be reviewing a lot of these methods shortly. The tree set gives us a lot more functionality, but at a higher cost compared to a linked hash set, or a hash set. You don't really have to understand the underlying data structure to understand two important points. Elements which implement comparable, said to have a natural order sort like strings and numbers, can be elements of a tree set. If your elements don't implement comparable, you must pass a comparator to the constructor. Okay, so hopefully you've got a picture conceptually of the three types of set classes Java offers us. Let's jump into code and start exploring the tree set class and how to use it. I won't spend much time on the linked hash set since it doesn't differ significantly as far as functionality from the hash set. Just know that the linked hash set provides a predictable iterable order, and this incurs slightly more cost than a hash set because of the doubly linked list structure that supports it. Okay, so I'm using the Sets and Maps project. I want to create a new class, apart from the main class, to keep the tree set code separate, so I'll create a tree set main class in the dev.lpa package. I want a main method on this class. Next, I want to use the phone and email lists from the contact data class. I'll set up two local variables, both lists. The phones variable will get assigned the result of calling get data on contact data, passing phone as the type. I'll retrieve emails by passing email to the getData method. If I want the additional functionality of the sorted set or navigable set, then I need to declare my set as one of these two types. I'm going to start out using the navigable set as my reference type, the most specific of the interfaces, because I want to cover all the methods unique to both the sorted set and navigable set. I'll call this variable sorted and assign a new tree set, passing it my phones list. I'll print the elements in the set. This code compiles, but if I run it, I get a familiar error that contact cannot be cast to class comparable. This exception confirms what I stated in the slides, that elements must implement comparable. I can get around this requirement if I pass a comparator to the constructor defining the sort, which I'll do next. The constructor that takes a comparator is a single argument constructor, so I'll create that, then add my phone contacts. I'll comment out that first statement. Before the for each statement, I'll add a couple of lines. First, I'll create a comparator of type contact called mySort. I'll set that to the result of calling the comparing method on comparator using the method reference getNameOnContact. I'll create a navigable set of contact and assign a new tree set, passing my comparator to it, and then I'll call addAllOnSorted to add the phone contacts. Okay, let me run that. And now you can see my phone contacts in name order and without duplicates. Since we know strings have a natural sort order, I'll create a tree set of those next. I'm using the noArgs constructor in this case. I'll loop through my phone contacts, adding each name of the contact to my set of strings, and print them out. Running this code. And you can see that my justNamed set has been output in sorted order. I can also pass a sorted set to the tree set constructor, and since I already have one set up, sorted, I'll pass that. I'll create a new set, another navigable set, called fullSet, and assign that a new tree set, passing my sorted set to the constructor. I'll call addAll to add all emails and print the elements out. This compiles and runs and shows that I now have a combined list of contacts in alphabetical order. In this case, the sort was determined by the sort mechanism of the tree set passed to the constructor. In fact, there's a method on the sorted set interface that returns the comparator used in the set. I'll create a list called fullList, assigning that a new array list, passing it my phones list. I'll add the emails to the full list using addAll. I'll sort the same way the tree set is sorted by passing the result of calling the comparator method on the sorted set, and then I'll print my combined list and running this code. We get this list that contains duplicates, but I was able to sort in the same way as the set alphabetically by the name. Next, I want to show you the first, last, poll first and poll last methods on this class. But before I do that, I also want to get the minimum and maximum values of the set. You may remember there are min and max methods on java.util.collections, so I'll try to use those first, passing the full set to those methods. First, I'll call collections.min passing full set, then collections.max. As you can see, this code doesn't compile. That's because I still haven't implemented comparable on contact. But there are overloaded versions of these methods that let me pass a comparator, and I can actually get this from the set itself, as I showed you earlier. I'll add fullset.comparator in both of those method calls. This code compiles and runs, and I'll print the results shortly. But actually, the sorted set interface includes first and last methods, and I'll demonstrate those next. I'll create two variables, both contacts, and I'll set first to the result of calling the first method on fullSet. For last, I'll call fullset.last. These methods give me the same results as the methods on collections and are the preferred way to get this data. But I did want you to see the alternative, which you might see in legacy code. I'll print these out next, printing the name of the min value, then the name of the first variable. And I'll do that for max and the last variable too. Running this code now. You can see both elements are the same, meaning min and first get the same element, and max and last also get the same element. In addition to the first and last methods, there's also the poll first and the poll last methods. These remove the first or last sorted element from the set, and the methods return the removed element. To test this, I first want to create a copy of the set, so I'll create a new navigable set variable called copied set, setting that to a new tree set with the full set passed to the constructor. I'll print out what I get back from executing poll first and do the same for poll last. Then I'll print all the set elements and a separator line. Running this code now. You can see I get the same result as I did with the first and last methods, but with one very important difference. The elements are first removed from the set, which you can see here. When I print out the elements in the copied set, Charlie Brown and Robin Hood are no longer in the set. Okay, this feels like a good place to end this video. I've introduced you to the tree set, which implements both the sorted set and the navigable set. This set has first and last methods, which retrieve the first sorted element and the last sorted element respectively. The poll first and poll last methods do the same thing, but in addition, they remove the element from the set. In the next video, I'll be covering additional methods unique to the navigable set, as well as a few on the sorted set interface. I'll see you in that video.